physics, so I'm looking to find the definition for the equations in the physics. I want to know that how to use the mathematics and the physics. So a wide range of the research I do actually, cosmology, modified gravity. I divorced from the gravity, so now I'm the single person. So I'm working only on the mathematical physics and a little bit about the ADS-CFT and string theory, but in the sense of the applied string theory something. But today talk is about my new work. So I did this work with the collaboration with my internet colleagues. Professor Laga is from Michigan University, one of the highly cited mathematicians in the whole history. So I think he got around 64,000 citations for his papers. So he's a specialist in the special function, and he's doing a lot of mathematics. So the work started by my interesting to know that what is the generalization of the zeta function. So I will explain to the audience that what's the zeta function. Some of you are familiar with the zeta functions. So my motivation was that actually at the summer I was interested, before the summer I was from the March, I was interested to know that which kind of the solution remain unsolved. So I find that the Riemann hypothesis or Riemann conjecture as an unsolved problems. And eventually I found that this Riemann zeta function, it could be related to some phenomena in statistical physics as we know. And this phenomena is Bose-Einstein Condensation. So to understand, to be familiar and friendly with my talks, so you needed to know that I started from the pure mathematical problems, Riemann hypothesis. So it's $1 million prize problems. I didn't got the money, but I don't know. I wish to get.
You wish to do that?
Yeah, of course. As long as I be alive. So I was looking for the application of zeta function, so I came to the Bose-Einstein. So I was studying that, and I used it in my lecture, so I was familiar with Bose-Einstein. And eventually I found that if you a little bit make softer this conjecture, so you can have some idea about the solution for that. So the idea came to me that maybe it's interesting to study a new class of the Bose-Einstein condensations, gas, bosonic gas. And the work stopped here, so the work finished already there. So after that, I was found some fact about this new soft version of their zeta functions. And I found that these functions are satisfy some kind of the partial nonlinear self-adjoint differential equations. So you are able to explain the mathematics of the mathematics involving in this phenomena using a pair of the creation-annihilation operators. And they are new actually. Like what you are doing in quantum mechanics for the normal harmonic oscillator and what you are doing everywhere. And eventually we find that using this pair of the operators, you can define a hypothetical particle. We call it this Lerch tone, but actually, and we estimated the mass for that, the lower bound for that. And the lower bound for this particle, which is responsible for this special type of Bose-Einstein condensation, is in the order of the mass which the people before find that for some kind of the bosons. So that was the plan. Everybody should know that what the other people do, I think. This is our role. So before I go to the detail of math, I want to tell you that when I came here in September, so I continue my work like before, of course with lower rate because this coordinator job is killing any research. Anyway, I work it. We produced some papers in the journals, normally with the journal more than impact factor 3 or 4 or 5 something. So the interesting was that in the first semester also we published one paper in Scientific American. So about my first paper here. And there are some other statistics here. I don't know what to show you. Anyway, so I start from the beginning. So this slide and the next couple of slides are familiar with most of you, so I just want to pass it very quickly. So what is we calling Bose-Einstein condensation, or they call it the new phase of the matter, is just the state of the matter at a very low temperature, and the matter should be the component of the matter should be the bosons. And the phenomena is that when you reduce the temperature below some specific range, which is called critical temperature, all the particles wanted to sit in the ground state. So you will have a ground state in your system with a large number of the particles, and this phenomena is called Bose-Einstein condensations. And the other important things about this phase of the matter, this new phase of the matter, is that at this phase the particles are strongly correlated. So and the distribution of the particles are in the coordinate and momentum both. So you know that in the field theory and in the scattering, always you can find the distribution or cross-section of the particle during the scattering phenomena, and the distribution will be function of the momentum only. Yeah. P is the only parameter which appear in the distribution of the particle, because basically from a mathematical point of view, you use the Fourier transformation, so that's over the momentum. So you will get the cross-section or something as a function of the momentum. Even you can see that in the classical physics. But the Bose-Einstein condensation density or distribution comes from the coordinate and momentum. So that's make the problem harder. And the physics from the Bose-Einstein was known before from the work of the great Indian physicist Bose. So I bring a paragraph from his biography actually. He invented this phenomenon, not exactly that, a softer version of that, when he was teaching in the Dhaka University. And he wrote, he was not able to be sure that about the derivation which people use it. Sorry, this is the letter he wrote to the Albert Einstein. And he reported to the Albert Einstein that I find that something maybe is interesting for you. So Albert was a very gentle person, so really gentleman. His door was open to anybody or any talk. So Bose wrote that this calculation is written in English, so I wanted to publish it in the good physics. So can you translate that for me and publish it? And the Einstein did it. So he translated his paper and they published it with his name, the Bose name, in the Annals of Physics. The name of today is Annals of Physics for Physics. So this is the low quality version of the first page of the Bose paper. So now we pass to the statistical mechanics. How you describe the Bose-Einstein condensations? So in statistical physics, any textbook, standard textbook, you can find it that if you consider the bosonic gas in grand canonical ensemble, so you can write down the partition function for that, and using the partition function, you can calculate the average of the particles in each energy state, so you can find that the density of the particles in any state. So by any state, I mean just two classes of the state. One is the ground state, and this is the important one. The VIP state is the ground state, because this is the state which all the particles want to sit there in the low temperature. And there is another one, this is excited state. So by basic statistical physics, you can find it that the number of the particles in the excited state will be proportional to this expression. Here n is the total number of the particles, T is the critical temperature. Critical temperature is a function of the mass of the particle, and also it includes the Planck constant. So when I say that the critical temperature of Bose-Einstein gas involves the Planck constant, so you can dreaming that maybe there is some classical limit for Bose-Einstein. And that just saved this word from me, so I will use it that. So later I will show you that there is some classical limit for Bose-Einstein condensation. So this paper already is in our archive, so you can also find more detail on that. So I will start from the grand partition function. So you will see that this is here you have the sigma over the energy levels, and beta is just inverse of the T. And Z, the fugacity is is related to the chemical potential as you see it. And we are lucky that in bosonic systems, this factor, Z exponential, is always less than 1 for any energy level that is upper the 0. So, you remember in the last slide that the grand partition function was given as a summation over the energy state. So we use a fact in the statistical physics several times. We use this fact that we say that for enough large volume of the system, the spectrum of the particle roughly converge to be continuous. So I mean the spectrum of the energy of the particle almost will be a continuous quantity. So you don't need to think about the Bose-Einstein condensation like a phenomenon of occupying the energy state, like the discrete energy state of the hydrogen atom or something. You can think about the band of the energy, and this band is continuous. Any energy you can read it from here. And the reason to pass from the sigma to the integral in the calculation of the ground state, ground partition function is that normally for many systems, what we are talking here about the particle in the box. So particle in the one-dimensional quantum mechanical box, the energy is given in terms of the n is the principal quantum number and v is the volume. And you, by just the simple algebra, you see that if just you think about the thermodynamical limits, if you take the volume of the system very large, as we are doing always in the statistical physics, so the difference of the energy state tends to the 0 at the limit. So what I promise you that we can use it that, so you can consider not the discrete level of the energy for the bosonic system, you can continue to think about the continuous spectrum of the energy. It's very essential point. This is very essential point. The pass from the sigma to the integral. You know, it never happened in the fermionic systems. Never happened. It's only happened in the bosonic systems. So the next step is that how to evaluate the integral. So to evaluate the integral, you need a concept, we call it this density of the state. You needed to, from the mathematical point of the view, from my favorite point of the view, you needed to define the integral by the weight. So you needed to have some weight here. So you cannot do the integration here without the consideration of the dimension or something else. So the function which makes this balance to you and make it the mean, give the mean to this integral is called the density of the state. I will back to that. I will back later to that. So I was thinking that which kind of the density of the state maybe would be interesting. Because I was interested, I told you, to generalize the zeta functions. So this kind of the density of the state is the density of the state of classical, I mean the non-relativistic particle in the one-dimensional, in the box. So the density of the state is proportional to e power 1 over 2. So, and this actually gives you the weight to the particle in the range of the e plus 2 delta e. So this is the weight of the particle. So you needed to put this factor inside the integral to make it to give the mean to this integral actually. So there is a parameter here, c, and I don't talk about that now. So a few minutes later, you will see that this C played a very essential role in our study. So far from today, from this moment, I wanted to study the Bose-Einstein condensation for a type of the bosonic system with this density of the state. You see that if you take the limit from that, if you set C0, so you cover the normal Bose-Einstein condensation. You can find the detail in any book like Huang or Patria or anything. So the next step is that we use the basic statistical mechanics, calculate the pressure and number of the bosons. So thanks to these assumptions about the density of the state, so this is the standard expression. So there is no any advanced mathematics here. I just used it. I just expanded the integral, but with one expectation. There is one case you needed to be very careful about that, and the case is that the case with the energy epsilon equal to 0 should be considered separately. There is a explanation for that. Note that by substituting, if you substitute the if you just want to formally integral that and forget about the terms with epsilon 0, it means that eventually you give away to the ground state incorrectly. So you need to, this is what we are doing a standard calculation of Bose-Einstein. We separate the portion of the epsilon 0 from the rest of them. So you see, when you exclude the epsilon 0, so you need to start from the after the 0. So I put this plus here to say that just the integral will be evaluated after that, after the ground state. So there is a standard expression gives you pressure and the end. So if you be able to evaluate the integral, you can get the equation of a state. And you can get information about the phase of the matter, which you have here. So there is a small block here, just to be remembered that if Z, the fugacity, which is exponential of the chemical potential, be very, very smaller than 1, so the last terms are all on the order of 1 over n, and if Z increasing, and especially when Z tends to the 1, this factor, which appear here, and this is actually this is n over v when you just calculate that for the epsilon 0, and we call it this n or n0 over v. This factor will be equal to the n0 over v, and n0 will be larger than n, and this phenomenon. This is a mathematical explanation of the Bose-Einstein condensation. Bose-Einstein condensation happened because of only this term. When the Z tends to the 1, so this term diverged. So it means that you can have a lot of particles in this state, in the state of epsilon 0.
N0 is number of particles in ground state?
Yeah, exactly. Per volume, actually, per volume.
Okay.
And also, what if you decrease the temperature, so the same second term will vanish, right?
Yes. You mean here? This term will be ignorable. I mean,
you are talking about chemical potential, but
chemical
if you decrease
potential,
the temperature, you let beta goes to infinity. Then
beta
again,
tends to the minus infinity, actually.
Then again, you
Yeah.
get the boson condensation.
Yeah, you can have it. Yes, actually, that's very low temperature. Actually, you can recover. But the ground state particle do not have any contribution to the pressure, and that's important. So I mean, you cannot detect the pressure for the ground state in some kind of the Bose-Einstein matter. So there is no any mechanical experiment you can do that and define the pressure. All comes from the n. So n is the things which to evaluate the integrals. These integrals are very complicated. If you set C0, so the result is presented before in the literature. It's called a Zeta function, and it's very familiar actually to the community. And this is what the standard Bose-Einstein condensation. But if C is not 0, this parameter, this free parameter, there is no any fine tuning or something about this parameter. This parameter just introduce it, and you will see the effect of that later. Yes.
So in a plain language, you can say that the number density, which is n upon v,
Yes.
almost grows up at the VDC.
Only at the limit of the Z tends to the 1.
Like that.
Yeah. At the boulder. And
Yes.
this boulder is translated to the existence of the critical temperature.
Yeah.
Yes, exactly. Very good. So that was the work which I told you, the logarithms. So I find in the literature that such kind of the integral studied as a generalized Bose-Einstein function or generalized Zeta function, and they call it Lerch function. Lerch was a French mathematician.